So in this particular lecture, what I will do is to talk about the mechanism of mediation analysis. And for that mechanism, we have a situation like this where we have a exposure variable. So in our example, our exposure variable was osteoarthritis. We have an outcome. In our example, our outcome was cardiovascular event. We have a mediator known as the pain medication, and we had a number of covariates such as age, sex, and other variables. So this is the DAG for our mediation analysis, and based on this DAG we are going to explain the process or mechanism of performing a mediation analysis. I'm going to talk about two different approaches based on which this analysis can be done, but in the lab I will just show one of them, because I think if you understand one process you can also think about how to work with the other process, but it is probably a good idea to focus on one approach so that you get a good grasp on that method first. But I should warn at the beginning of this video that the process is quite involved and you have to be a bit careful about some of the notations that I'm going to show here. And after you are done with this video, you can try to look at the lab video, and in one of the lab videos I'm going to explain exactly what I am showing here. All of the equations that I show here will be shown in our labs, so that it will be a bit more clear for you in that lab what I'm describing here now. Alright, so the problem that we have with the counterfactual definition is that we cannot observe both. And this is not particularly a problem for mediation analysis. It is also a problem when we did our total effect estimation, right? When we have a counterfactual, say for example, remember in one of the labs I talked about John taking the drug, and then we followed him for 3 months to see whether his cholesterol level dropped or not. And then we had a time machine, and then when we went back in time and then again followed John, but this time he did not take any cholesterol reducing medication. And then we followed him for 3 months, and then we observed that outcome. So we are working with two different worlds. In one world, John takes the medication, and in another world, John does not take the medication. And if both of those worlds existed, we would know what happened at the end of those 3 months under treatment and not under treatment. And then we can simply compare the outcomes to see whether there was any effect of that drug rosuvastatin to reduce the cholesterol level. But think about our real world scenario where we actually cannot observe the same person twice unless we are doing some sort of crossover trial or something like that, which we are not really doing here. We are working with observational data, and we can only observe a person under one condition: whether he was exposed or he was not exposed, right? And the same theory applies for the mediation as well, where we cannot observe two outcomes under two different mediations, or whether this person takes pain medication in our example, and whether the same person does not take the pain medication, we cannot really observe the outcome of that person directly. So remember in the previous video we were talking about in mediation analysis we basically have equivalence of two exposures. So this is our outcome y, and this is our main exposure, and this is our another exposure, say, which is also affecting our y. So we are essentially dealing with two different exposures here. So our counterfactual definition got complicated. Now we are comparing, instead of just treatment, we are also comparing with respect to our mediator. So we are basically comparing A versus A naught and M versus M naught. But again, the same problem of the counterfactual, that we cannot observe a person's outcome who is treated and takes the pain medication versus the same person's outcome who was not treated and takes the pain medication. So we cannot really observe that in a real world, because we cannot go back in time to observe the same person under two different conditions and record their outcome twice. And when we are trying to get the direct effect, not the total effect, we are just trying to get the direct effect. The idea was that we simply have to fix our M to allow our exposure variable to change, right? But in a real world, we cannot really have same M and then allow the person to take the drug and not take the drug in the same timeline, so that we can observe two different outcomes under two different conditions. So to allow us to understand how we are going to do this kind of analysis using the counterfactual definition, we are essentially modifying our DAG to make our understanding or implementation of the DAG in our modeling stage easier, right? And this is an idea that I have seen in one of the workshops, and I will cite that workshop at the end of the talk, where they're essentially talking about assuming that there are two different exposures. One exposure is directly responsible for the direct effect, and see that A has nothing to do with M directly, and assume that there is another A that has nothing to do with Y directly but has to do with M. Why we are doing this? Because at the end of this analysis, what we will do is we will use this red A to get our direct effect, and then we will use our A star or this blue A to get our indirect effect, right? So even though we do not have two A variable, we have just one variable, we are just doing it so that we can implement our model in the way that can give us our direct effect and indirect effect. So essentially what we will do in a nutshell is that we will actually create two copies of A. That means we are in a in the implementation stage of this concept in the data. We're essentially going to copy the data twice, and then we will try to address the consequences later. So it's like when people say there is no free lunch. In this, what we will do, we will eat the lunch first, and then we will think about how to pay for that lunch. So in the process, when we are making two copies of the data, what will happen is that we will essentially disrupt our variance estimation process, because we're essentially copying the same data twice. So that is, when we are copying two sets of data together, we are essentially, what we are doing is we are eating the lunch, and then we will do some other process to get back the variance in a reasonable way, and that will be more about paying for the lunch. So we will eat the lunch first. All right, so here we go. So in this first step, what we are going to do is we are going to explain the mechanism into 5 different steps. I started with step 0. It's like Python coding. Your index starts from 0 in Python, and you are starting from 0 and you will end at step 4. But there are 2 different approaches that we are going to use in step 3 and 4. So in this first step, what we will do is we will essentially prepare our dataset with y, exposure variable, mediator variable, and all of the necessary confounders. So remember, in our case, our y was cardiovascular, osteoarthritis, pain medication, and our C was age, sex, income, and all of the other confounders we have already identified. And this C variable does not have to be one variable, it can be many variables. Once we set up our data, then we replicate our exposure with the same exposure. That means that we are not really changing anything in our dataset. Whoever was exposed, we keep them exposed. And this is something what we call the facts. That means that we are keeping the data as it was. And then what we are doing in step 2 is that now we are going to build a copy of the original data, but this time what we will do is we will change the exposure variable. And how we are going to change the exposure variable? We are going to set all of the people who were exposed to unexposed, and all of the people who were unexposed, we will set them to exposed. So this is basically what did not happen. This A star is basically what did not happen. So we are calling them alternative facts. Whereas in our step 1, this A star was our facts. That means what actually happened. Whoever was in the treated group or exposed group, they were in the exposed group. Whoever was not in the exposed group, they were not in the exposed group in the A star either in step 1. But in step 2, we have changed that. Exposure went to unexposed group, unexposure went to exposed group. Alright, so what is the implication of that? So that will become apparent later on. So in step 3, what we are doing is that we are essentially working with 2 different models, and you can pick one of them. This is the imputation model and this is the weighting model. So in our lab we will only show the weighting approach. We are not going to show the imputation approach, but this is very simple to understand what is the imputation approach. And our choice of either going to either imputation or weighting will also change how we approach our step 4. Because if you take the imputation approach, then there is one way to approach the step 4. But if you take the route of this weighting, then obviously our final outcome dataset will be different, because that dataset will be then weighted, right? So let me give you a very concrete example of what I'm talking about, because it may seem a bit weird of all of these steps and what is it really doing, right? So in this stage, let us just work with the dataset. So we are just setting up the dataset and we are identifying which are the subjects we are going to incorporate, which is, say for example, for in the purposes of this example, we are just going to stick with one C. We are not going to show too many C's. This is just for illustrative purpose. So we have C variable, M variable, A variable, Y variable in our data set. So, and this is the format of our data, and we are just showing you the data for 2 persons. There are obviously more persons, but I'm just showing you first 2 persons data set, where this person was, say for example, this was younger age, this was older age, this was no pain medication, yes pain medication, this was osteoarthritis group, this was the control group, and say for example this was some sort of measurement from the cardiovascular, and this was another measurement from the cardiovascular, which is basically our Y. In our example, obviously cardiovascular event was the binary variable, but for the purposes of illustration, let us just consider this Y as a continuous variable. Alright, now we are in step 1. So see what is changing in step 1 is that from the previous slide, all of the variables are same, but the only thing that is different here is that we are adding a star variable, right? And how are we calculating this a star variable? We are basically copying whatever a values we had. We are basically copying, nothing else. And this is our step 1. And in our step 2, what we are doing is that we are setting alternative facts. That means whoever was in the osteoarthritis group in the original data, now in the step 2, in this additional duplicated copy of the dataset, every other dataset is exactly the same. Only thing is that we are adding this a star, where this a star values are opposite of what was in the original a value, right? So remember what is the difference between step 1 and step 2? In step 1, we are basically creating one variable more, one a star, which is basically a copy of our original variable. And in step 2, what we are doing, that we are duplicating the same person's data, but only change is that our a star values are going to be the opposite of original a value. Notice that there are 2 other components or variables that we are dealing with here. One is the y variable and one is the w variable. So this y variable, this question marks are coming from this data, because we do not know what would happen as an outcome for this person when the data was the exposure group was 0. And also for this person, I don't know what would happen with the outcome if the exposure group was 1, because originally the exposure group was 0 and we observed 50. That was not a problem. But under exposure group 1, when the person was actually treated instead of not being treated, then what is the outcome? I don't really know. Alright. Similarly, this is for the imputation approach that we are going to use later, and this is going to be useful for weighting approach that again we are going to use in the 3rd and 4th step. So in the original data that we have, our weight is 1, so there is no change in the weights. But what is going to be our weight in the duplicated data, that we do not know yet, so we will have to calculate that part later on. Alright, so first let's talk about the imputation approach, and then we will worry about the weighting approach. Let's just get this imputation approach out of the way first. So in the imputation approach, what we are essentially trying is we are trying to impute these question marks under the y values, right? So to do that, what we are basically doing is that we are sticking with our original data. What is our original data? This is our original data. This is our original data, where we have observed our y. So that part is our original data, and in the original data we fit a outcome model with respect to A, M and C, right? And then what we do is predicting from the built model, whatever model fit that you have, you are predicting from that, but you are then changing A to A star. So you are not using this A value anymore. You are now using this A star value in the new data set. And then this equation or this fit, the model was selected by the original data, but when we are predicting from this model, we're essentially using A star instead of the original A value. In our original model we had A. When we're predicting, we're essentially changing that to A star value. And then this will give us a reasonable estimate of these Y values, right? So one thing that is very important to understand is that we are fitting our model in the original data and we are imputing our data into the new data. What is the new data? Whatever was associated with these blue numbers or the rows with question marks in the Y. So those are the new data. And then based on this fit, we will get some values of these question marks, right? Say for example, when we fit, we essentially get 70 or 60 for those question marks in the step 3. So once we have our complete Y values, right, then what we do is we fit our final model in the entire data set. And what is the final model? Our final model is Y is the outcome. We have A star, and we adjust for the confounding variable C. What does that mean? That means that whatever coefficient we get associated with A is going to give us the direct effect. Whatever coefficient we get associated with this A star will give us the indirect effect via the M variable. So that is the interpretation that we will get out of this regression. And this explains how the imputation method works when we are dealing with the mediation analysis. Alternatively, we could work with the weighting approach. Remember these W's? We have not used anything, or we have not explained anything about these W's. We were only concerned about inputting these Y's, and we got our direct effect and indirect effect from that. So we are again going back to step 3. We are not in step 4. We are going back to step 3, where we are fitting our mediation model with respect to exposure and the confounder using the original data. This is not the entire data. This is just the original data. We have not duplicated anything. So whatever question mark rows you have here, we will just delete them, and we will only work with the rows that were associated with one weight or non-missing Y values in here. So we fit the model in the original data, but when we predict, we use all data. What does this all data mean? That means not only the old data, but also the new data associated with this question mark, right? And there are two different predictions that we are dealing with here. The first prediction we are doing, where we are replacing all of the A values with our A star values, and then in the second prediction we are essentially using the same model that we used to fit the original data, and that will give us some prediction, some particular value of the probability or risk of M, and some prediction value of the probability or risk of M, right? So these are basically going to be the fitted values. So then what we will do, the fitted value of this divided by the fitted value of this will give us our W values. So whatever W values we get here, we will just put them here, and you will see this will be 1, but this will be something different than 1, this will be again 1, and this will be something different than 1. So our W values will look like this. So once we have our W's, what we do is we again fit the same model that we have fitted in the step 4 of the imputation approach. But this time what we do, we weight our model with W. But one thing that is different than the imputation approach that we have used earlier is that we are not changing our Y values. We are keeping the original Y values that we have observed. See, original Y values that we have observed. The only thing we are changing is the weight of this based on this weighting approach, right? Previously, I'm just going back and I'm showing you in the imputation approach, we were changing our Y values based on the model fit that we got in the step 3, right? Whatever value we got from the model fit, we were just inputting those values in here. But in the weighting approach, what we are essentially doing, we are essentially keeping the same Y values. We are not changing these Y values. We are keeping the original Y values for that person. The only thing that we are doing is we are calculating these W values. And then when we get this weighted regression, weighted by this W, we have A star and C, similar to our imputation approach. But in the imputation approach, we were not really weighting. We were changing our Y's. So the interpretation of this model is, however, the same. Whatever coefficient that was associated with A is going to be the direct effect. Whatever coefficient that was associated with the A star is going to be the indirect effect. Okay, so I have just explained 2 different ways to do the mediation model. The first one was the imputation model, and the second one was the weighting model, right? Okay, so in the process of duplicating the data, why did we duplicate the data? Because we wanted to get the direct effect and indirect effect. So we duplicated the data. So we ate the lunch that was not free. Why it was not free? Because in the process, the standard error gets distorted because we are essentially dealing with double observations, new and old, from the same subject. So how can we rectify this? We can try to find the robust standard error by using the cluster ID. What is the ID? ID of that person. But a more appropriate way would be to simply use bootstrap. But only caveat is that you have to pay the price of computing time, because you have to choose a large number of replication to get a reasonable estimate from this bootstrap. All right. And also, it is certainly possible that your mediation model could have some non-linear relationships other than only the confounder variables. It could have some sort of interaction between the A and C, and it could have some polynomial terms of some of the C variables as well. One last concept that I want to explain in this particular video is that of proportion mediated. So proportion mediated is a concept that gives you an idea of the proportion of effects that is being mediated by the mediator. So basically the formula is indirect effect divided by the total effect. So whatever odds ratio you get for the indirect effect, log odds ratio, and whatever log odds ratio you get for the total effect, when you divide them, you get the proportion mediated. And this proportion mediated is actually a very useful concept for you to explain the proportion of effect that is being mediated by the mediator. So is your mediator responsible for 50% of the effect, or is your mediator responsible for only 10% of the effect, or is your mediator responsible for 80% of the effect? Which is it? Like, is direct effect more or the indirect effect more? So this proportion mediated effect, or PM, is a very interesting concept in terms of when you are trying to do the interpretation for the mediation analysis. But when you are doing this proportion mediated calculation, then the question is, what should be your confidence interval? Again, it is possible to calculate the confidence interval for the proportion mediated, especially when you are doing the calculation using Bootstrap. It is very easy to find the confidence interval for the proportion mediated.